John Chowning needs no introduction, actually, but you know, he has such an amazing catalog of music and research, and we only have 45 minutes, so we're going to try to condense this as much as possible, but I want to get to some of the things that you're excited about talking about, too. I was hoping that maybe you could start out the conversation just telling us about your musical life pre-Stanford. So before you became a doctoral student at Stanford, you spent some time in Europe and you were exposed to some different things. So if you could just tell us a little bit about that.
Sure. So in 1959, having graduated from Wittenberg University in Ohio, where I went on the GI Bill, went to school, studied music, I went to Paris to study with Nadia Boulanger, who was well known in the United States as a teacher of composition. And my 3 years in Paris resulted in some very good teaching from Nadia Boulanger, but perhaps more importantly, some wonderful experiences in new music. In 1959, 1960, 61 were years where Paris was kind of like Berlin today, maybe the center of lots of experimentation. And one of the concert series, which was very attractive, and at which we heard much new music, most of Boulanger's students went and hissed and wooed. I didn't, however. I listened with care. That was the Domaine Musical that Pierre Boulez had started at the Théâtre d'Odéon in the middle of Paris, where I heard pieces, for example, by Stockhausen, Contacta, Berriot, Circles, Henri Bousser, Trois Visages de Liège, many works that were based upon electroacoustic means. So I came to Paris, left Paris after 3 years and went to Stanford to study music composition, never having seen a computer, never having had a really math course beyond high school algebra, and discovered Max Matthews' article in the November issue of 1963.
Can you tell us quickly a little bit about Max Matthews and his research, just for people that don't know?
Max Matthews was an extraordinary researcher, scientist, engineer, scientist, I would say. And not long after he began his work at Bell Labs in 1956, I think, he began experimenting with computers and music and wrote this article, The Digital Computer as a Musical Instrument, published in 1964. But his work began in 1957. And Bell Labs at that time, and back for probably a period of 40 years or 50 years, was probably the greatest concentration of engineering, scientific brain power on Earth. The communication satellites, John Pierce, the laser, the integrated circuit. All these inventions came from Bell Labs. One of the most important bits of work, however, was by Claude Shannon, who was a mathematician. And in Max's article, he makes this statement: a schematic diagram of this process is shown in Figure 1, or he shows this image. In this article, as I said, filled with technical jargon, which I didn't understand, but was explained by this diagram, which got my attention because the diagram suggests that if you have a computer, can produce numbers fast enough, which numbers are accurate enough, you can convert it into electrical energy, send it to a loudspeaker, and produce any sound that a loudspeaker can make. So this idea told me that if I could learn to program a computer, I could produce any sound that a loudspeaker can produce. And based upon my experience, just as an ordinary listener, I knew that loudspeakers in recordings could produce lots and lots of sounds. And I was interested in exploring the world that I had first met in Paris just a year or so before. So this was the open door. This was the invitation to those of us who were interested in electroacoustic music, who hadn't the experience that required this is the Cologne studio, I think. This is the Milan studio, the guys in the white coats who were the engineers who knew everything and were frightening whenever I met them, I found, because they knew more than I did, but they didn't know about computers in those days. So in my first work, I realized that I could do with a computer what many engineers with much time could not do with the kind of equipment and skills that were available. So the key was learning to program computer. This is important because everything that we do with mobile devices, iPhones, listening, concerts, is based upon this sampling theorem. And Max says, mathematically it has been established that this conclusion is correct. That is, the sampling can create any waveform. This was the citation, the first one in this article. This was the first public article about a systematic production of music using computers. And there it is, Claude Shannon, information theory. And if you had ever wondered where the word bit came from, it's in the sampling theorem 13, where he wrote, if the base 2 is used, the resulting units may be called binary digits, or more briefly, bits, a word that one of his colleagues, Tukey, coined. So I began, and Stanford was a university that was open to this experimentation. That was in 1964.
Was this typical for music students? Because you were working kind of across departments, right? You were working with the math department and with the AI department and computer science. And was this something that other music students were also exploring, or were you kind of an outsider in that?
I was an outlier.
Outlier.
Yeah. And, but Leland Smith, about whom Andre spoke, supported this work. He thought that was worth exploring. He understood, I think, exactly what the importance of this idea of sampling was to possible music. In those times, I worked on the artificial intelligence lab computer, late hours, like graduate students do, and I was able to get free time in the wee hours of the mornings and weekends and pursue these ideas, the first of which was spatialization. Mm-hmm. I'd been quite taken by the work of Stockhausen. I'd performed Kontakte as a percussionist, and Gesang der Jünglinge, of course, which is a classic in the genre, both of which make a use of space that I found very powerful and compelling, and an idea that I wanted to explore using computers. So that was my first project.
And so one of your early pieces, do you say Sabelith?
Sabelith, yeah.
That was finished in 1971?
Right.
And so that's the first piece to use FM synthesis,
right,
which you also discovered.
I also discovered on the way,
right,
in 1967, that by modulating a simple waveform at high enough rates, one could produce a complex sound. Now, how did this come about? Why did I do this? Because in spatialization, I needed a sound source that would be distinctive from the reverberant field. And one way to do that, of course, is vibrato, change in pitch, to which the pitch is, the ear is very sensitive to pitch. As a child, I had begun with vibrato, or violin, so I knew vibrato as a performer. And so I experimented one evening, probably November 1967, undoubtedly in the wee hours, maybe 3 or 4 in the morning, which was typical. And so I'll show you kind of what it was I discovered and why I paid attention. Okay, so this is a sinusoid at 200 hertz, pure tone. Maybe a little bit more volume, please. Okay, so now we're going to hear the same tone, but now modulated in pitch, as in vibrato, plus and minus 10 hertz. Once more. Okay, now faster, deeper, plus and minus, now 100 hertz. So it goes an average of 200 hertz to 3, down to 100. Once more. So then I thought, well, what if I do it faster? Or deeper, actually. So now it's plus and minus 200 hertz, so from 200 to 400 to 0, and now faster. I thought, well, let's push it a little further. Now, I was still hearing pitch in time, and I thought about how violinists and mass work. I sort of knew that there were going to be limits, and then I thought, okay, well, I'll try it a little faster. And then I realized that maybe I'm not hearing pitch and time, but I'm hearing kind of a complex waveform. Then sort of tentative looking over my shoulder thinking, gee, I don't want to break the computer. And so I went still further. So this is now at 40 hertz, the same plus or minus 200 hertz. Well, that clearly is not pitch as a function of time. I'd crossed the boundary from time domain to frequency domain. Then further yet, 200 hertz. And I thought, well, wait a minute. What I began with was this. So it was the pitch with which I had begun this experiment, but was it distortion? Because in those days, loudspeakers were not very highly developed, and audio systems had all sorts of nonlinearities. And I thought, well, maybe this is kind of an artifact of the system. But I did more experiments and realized that it transposed, that I was hearing a complex wave using 2 oscillators that I imagine probably had maybe 8 or 10 harmonics, and they were harmonic. So I made differences in ratios of the carrier to modulating frequency, which I called center frequency and vibrato rate in those days, because I didn't yet understand the application of the mathematics of FM to what I had done. So with a set of examples, I went to an engineering friend and asked if this was some sort of unique, kind of surprising but interesting result. I pointed out that it transposed, it seemed to behave in a proper way, let's say. And so he took me to the term in engineering book, and we looked up the mathematics of the equation for frequency modulation radio broadcasting, and it all fell out and was perfectly explained. So that was the beginning.
Did you already at that time have kind of an understanding of the implications of this discovery, or was it just purely kind of intuitive? I'm curious about this. I want to use this for my piece, so I want to kind of figure out how to make it make sense for my piece.
Well, Holly, primarily the latter, because I had no experience in the world of analog synthesizers. So I had no idea. I knew that perhaps there would be an application in electronic organs, but this was far from real time. Each one of these examples, for example, probably took on the order of 10 to 20 minutes to compute a few seconds of sound. This was a time-shared machine, but so the more users, the slower the computation. And so there was no imagination of a real-time system as it finally turned out to be. So it was the basis for a piece of music. But it took a long time to kind of understand it. And I finished up the work in spatialization using FM as the signal source. And I can show you a quick example of that.
So did you also premiere that piece then in 1971
Yeah,
when you finished
1971.
And what was the reception like? Because this is an entirely new sound world, entirely new kind of timbral world for people, and then you play this alien music.
Right, yeah.
And so how did people respond to that?
So Stanford had no tradition of electronic music of any sort. And it was, people clapped politely. The next year I produced Tyrannus, which was kind of a full implementation of the spatialization and the FM synthesis, where I felt I was in control, and that was after, I began a graduate student in 1962, so in 1972 I finished Tyrannus, 10 years, and submitted it for that with the paper to the deans for promotion from assistant professor. And the question was, why, after all this work, you have only 2 pieces? I said, well, it was a lot of work, and I felt it was worth it. And
well, they do now too, I think.
Yeah, right. It was not. So anyway, let me just quickly show you what I accomplished in the spatialization. The idea was to create with a quadraphonic space, so surround sound. And I must say that I had lots of help. I asked lots of questions in an AI lab that was populated by engineers and scientists of various sorts, linguists, computer scientists, of course, and philosophers even. So any simple question that I would ask in trying to solve problems, for example, Doppler shift, etc., was easily answered by any one of them. So I had this kind of large resource, which this resource of people, and they were all infinitely patient and explained to me until I understood. And I implemented this in Fortran, a very powerful language of the day. And so the idea was just to be able to move sound through an arbitrary space, distance q, and angular displacement. So I could draw on a graphics display a pattern that would then, the computer would actually then compute the kind of controls for energy distribution between the 4 channels, Doppler shift, and reverberant field, etc. And we got a first patent, which was on this system, to realize this. And this was not real time, of course. And one of the things I realized that sound structure and music structure can be joined in a new way. That is, we can think about music structure at a level that begins with the signal itself and at some, let's say, acoustically intimate level. And the value of multidisciplinary environments, which is preserved, as Holly knows, at CCRMA with people full-time faculty in a music department who have PhDs in engineering, computer science, music, of course, now neurosciences. So this rich environment was very important to me and has been sustained by Chris Chafe, the current director, and his colleagues in a wonderful way. So here's a kind of a diagram of what I learned in those years about the problem or the complexity of perception of loudness and distance. So we hear a sound at a certain intensity that's close to us, and now we hear the sound far away. Do we hear it as being softer or the same loudness but at distance, or compared to a sound that's softer and close to us? What's the difference? Well, one of the differences is a change in centroid, kind of the weight of the spectrum. And here's an example of a sound beginning close to us and moving far away. So the overall intensity increases, but the percept that's really important is the fact that it's at a distance at the end compared to decreasing effort or force. So we begin at the same point, but now the centroid changes. So the number of harmonics, the higher frequencies with less strike force in this percussive-like tone. The harmonics, or the partials in this case, or the weighting shifts toward the lower frequencies. Now we compare the last two. Okay, once more, close but soft. Yeah, and loud and far. Okay, so that's sort of the sum of what I learned in those years in regard to perception and loudness, and it's been part of my way of working in the years that followed.
And so this was what you applied to your spatialization technique for Tyrannus in 1972. Okay, cool. And so you mentioned that you were up for review, and so you presented these FM synthesis and the spatialization technique and these two pieces. And so were you granted a promotion, or? I
was not, but that's okay. I was not given tenure, and it's not surprising. I mean, universities, like all big institutions, are very careful about the steps they take. Mm-hmm. If they're big steps, and this was a big step for any university, actually.
So at that time, then, you decided to do some research at IRCAM, right?
So coincidentally, Ligeti, who had been a guest composer at my last year of employment, from January to June of 1972, he heard what we were doing with computers. And when he returned to Europe, he invited me to come to Berlin here and present Tyrannus, which we did, and then to Darmstadt, and where I gave a talk about FM synthesis and played Sabalith and Tyrannus. There was a lot of interest, of course. Xenakis was there, invited me after to visit him in Paris. But the important thing is that Ligeti told Boulez to pay attention to what was going on in computer music in the United States. There was Jean-Claude Risset, of course, who had worked with Max Matthews, our father, at Bell Labs, was in Paris, but he too was kind of marginal in the scene. But Ligeti had a voice, an important voice, and Boulez, I think, paid attention and invited me and then later Max to be the scientific advisor. So it happened a year too late, but finally we persevered at Stanford and formed CCRMA in 1974, and I was then finally hired in 1979 as a full professor. So.
Okay, and that was shortly after the Yamaha license, is that correct?
The Yamaha interest, it began in 1972, 71.
Okay.
Yeah, and they had the foresight to dedicate a really strong engineering effort to seeing FM to a product. 10 years and probably 100 really good engineers. Wow. So the DX7 isn't Chowning's device, it's the underlying principle, and I worked with the engineers over those years, but it really is an instrument that belongs to Yamaha, and maybe especially Tomisawa, who had the idea for the feedback FM.
So just to fill you guys in that aren't aware, so John was able to patent the FM synthesis technology through Stanford, and then that technology was licensed to Yamaha, and they built a series of instruments before actually landing on the DX7, right? The DX7.
They had maybe 2 instruments, and then the DX7 was the big hit.
And you were pretty involved, I know you say that it's not your instrument, but you were pretty involved in the development and corresponding and helping out, figuring to find the best timbre for the different instruments.
Yeah, I explained all that I knew about, which was considerable by that time. I'd had some years working with it. And they were interested in a keyboard that would be commercially successful. They implemented it then in organs, not only the X7, that was the instrument that was well known in the synthesizer world. But their biggest sellers, of course, were electronic organs, which was a huge market for them. And finally, the largest application of all time was, of course, cell phones. And we've been at a concert of San Francisco Symphony where one of the cell phones rang, and maybe a ringtone from FM. And Maureen and I looked at one another.
So it's your fault. So you, let's see, around 1977 you finished a piece called Stria, which is one of my favorite pieces. Mm-hmm. Can you talk a little bit about that? You used the golden ratio for that piece?
So Stria, after Tyrannus, which has lots of inharmonic sounds, based upon a ratio of 1 to the square root of 2, which is a ratio that is far from it's not close to integer ratio, so it's distinctly not harmonic, the spectral result. So I was looking for other inharmonic possibilities, and I knew about the golden ratio from its use through history in many guises, and also some musical applications. I think Stockhausen perhaps used it at some point, and it's related to the Fibonacci sequence. And so after I was put out of Stanford, Ligeti had arranged for me to come here for a Deutsche Akademische Austauschdienst grant for a year. And I brought with me a few examples that I had generated with the computer before I left, one of which was sounds of the golden ratio. And so I kind of figured out the underpinnings for Stria at the theoretical basis while I was here in Berlin, 1974, 1975. So the concert last night, using the same theory that Mark and I worked on, was kind of coming home in a way. Oh, nice. Yeah, different roots, of course. Mark's roots were very different than mine, but that we met and realized a piece based upon this theory, which is easily seen. Okay, there's the golden ratio, which is this, where we are, this here, and it's related to the Fibonacci sequence. Adjacent numbers formed as a ratio approximate the golden ratio. But what was interesting to me was to create an analog of harmonic series and common practice tuning and scales. And so what I did is while in Berlin, without any sound sources, I worked on this theory. That's the one we know and love, and harmonic series. At the interval fifth, we hear an example. Should hear an example. Okay. So this is the golden ratio now, powers of the golden ratio as pseudo-octaves rather than 2 to the n, to powers of 2, and then a pitch division of 2 to the n over 12. In this case, I divided each of the pseudo-octaves, which are powers of the golden ratio, about a minor sixth, into 9 steps, and inharmonic partials, sounding with inharmonic partials. Some are many common partials, as, say, an octave and a fifth in the common practice tuning. We have this creation of spectra that have complementary relationship between pitch and space. Kind of what Andres explained. Pitch space and temporal space. In this case, it's pitch space and frequency space. Okay, so I then return to, let me move to, these are examples of combinations, but really this is the piece Stria, and just a section now worked as a composer works with sound. Well, we won't hear Stria. We heard something like it last night, but let me...
So how did you use the golden ratio in a different way for Stria than you did with Mark, or were you using kind of the same system?
So the same tuning system, the same spectral relationships.
You used for both pieces?
Yes.
Okay.
And in the piece last night. And so I gave, in a meeting in the autumn, Mark and I got together and worked out what the base would be, the common reference.
And how did you and Mark meet, first of all?
Mark was brought by one of our staff to Stanford, Mark Kars. And in fact, Holly encouraged me to talk to Mark.
Oh, I wasn't trying to shout myself out. So Mark Fell gave a concert at CCRMA, right? And then, he was I know he was really excited to meet you when he was there, and then was like thinking, oh, maybe I could collaborate with John, and I think he was in your ear, and then you were like, okay, and was so excited.
Sure. Yeah, as I said earlier, his roots are very different, and he came really from philosophy and playing as a kid with synthesizers, and mine were more formally educated, but I have a son who's 30 years old, Scott here, and I listened to all the music he grew up with, and he's a good horn player and a good jazz piano player, so I knew about pop music and I respected it because someone not only whom I love, but he's my kid, and he knew about music, and so I listened to what he pointed out, like Meshuggah. Listen to Meshuggah.
Oh yeah,
things like this.
That's a good reference.
And so I was interested in Mark's ideas, and we chatted and felt that would be an interesting kind of common territory to explore together with different roots. And I'm not religiously academic. As you know, we learn as much from our students as the students learn from us, in fact, maybe more from the students, because it's a highly dynamic and growing community of people. And what we do is we share the technology, and that's a rich experience for all of us. So,
Well, I think that's one of the things that really stands out also about your work in, co-founding CCRMA is it really is an open place and a place of experimentation. And, you mentioned that early on in your career, experimentation wasn't necessarily fostered by everyone, but that you had a few people encouraging you. But you've really been able to create kind of a haven for experimentation at CCRMA. So how did you manage to kind of imbue the culture there with these kind of values of experimentation and openness? And
so it was my experience as a completely naive but highly motivated student at the AI lab, learning from people who knew more than I and were willing to share. Then when I met Max, maybe a summer or two later, I went to Bell Labs and saw how Bell Labs worked, which was a laboratory design and where the researchers were told to leave their doors open, no closed doors in offices, so people could wander in and out. So as I did my work and we had the opportunity to teach this in the late 60s and early 70s, people were attracted to it from other disciplines, and I welcomed them because it had been such a rich experience for me. So John Gray, for example, from psychology, did his great work on timbre. Andy Moorer, who was a computer scientist, and he was actually the systems programmer, became interested in computer music because it's such a rich domain of application. Julius Smith was on the periphery and became involved, and of course now he's on the faculty. Chris Chafe later, Jonathan Berger, and now our faculty includes...
I encourage all you guys to Google all of these names later because they're all amazing.
Yeah. And Go Wang in computer science. So it's a kind of, it's obvious, the fact is. After my talk at Darmstadt, when Xenakis asked me to visit him in Paris, and he showed me the inchoate UPIC, his drawing device where he could draw. And he told me that, well, FM synthesis is kind of old because it's based upon sine waves, and that is Fourier, and it seems not to be forward-looking. And I said, okay, well, that's okay. I thought, well, this is a religious man, and with a religious view. And then he showed me what he was doing, and so he was drawing these arbitrary patterns on this, and then cycling through it at constant rate, and it was like, and he said, so this is the future. And I said, but you understand that this is all can be described by sums of sines and cosines because it's a periodic wave. And I said, also there's lots of aliasing. And I realized that he didn't understand some basic things about this medium. I mean, I highly respect his music, but the fact that I lived and worked in an environment where there were knowledgeable people in sciences who knew just from their basic training about acoustics, one had to always redefine what one thought, and you were being challenged always. So we learned that this environment can be not only productive from the point of view of art, but the whole intellectual enterprise is elevated because of these collection of disciplines where people talk, they feel free to talk, and there's no kind of implicit hierarchy, like someone who's a beginning student hasn't the same voice when it comes to an idea as a senior faculty. Everyone has a voice, and this was Bell Labs. This was the AI lab. And it's something that one doesn't have to work very hard to preserve. It's just it's so obvious that this is the environment and having a richness that one just naturally will preserve.
That's awesome. Should we ask questions now, or should we continue? Because we could talk about phone as well, and some of your voice synthesis stuff.
Yeah.
It's also super interesting.
But I also would like questions.
Questions. Okay, let's do
Sure.
questions.
We are about 10 minutes late, so
Okay,
Yeah.
so we can go over a little bit.
I guess it depends on karma. Karma may just switch us off.
I think that's okay. Did you?
Hello. First, thank you very much for coming. I have a question about the performance yesterday. I realized very quickly that by moving my head just an inch, I was totally tampering with the perception of timbre in a very complex manner. And once I discovered this, I just kept doing it the whole performance, basically. And I was surprised that nobody was doing it around me. Everybody was actually sitting very, very still. So my question is this like part of the way you compose the whole thing? Or what is the importance of the physical aspect and the ear? Or is it meant to be listened to in a very still manner?
Can you summarize?
Yeah, I'll just repeat that. So the question was, I'm sorry, I didn't get your name.
Theo.
Theo was asking that he noticed in the concert last night that when he moved his head, his perception of the audio changed. So he was wondering if that's part of the piece, is it intentional that people move, or he also noticed that a lot of the audience sat still. So what are your thoughts on people kind of moving during these pieces?
I would have been very happy to present this in a context where the audience was free to walk through the space. That's because of standing waves. And at certain frequencies of a half a wavelength, say at 1,000 hertz, is the wavelength of about 1/3 of a meter. So if you move your head a little bit, the spectral result will change. And I think it was more a byproduct because we don't know the exact acoustical conditions. We came into the hall. Mark defined the speaker setup and very carefully worked on the ambisonic part with Paul, whose last name I forget, but we shouldn't, from Karlsruhe. And so you do the best you can. And of course there are conditions which produce unique experiences, maybe in another space with the effect for the listener would be slightly different. But there were static sounds, and when that happens, then one gets standing waves, and then things begin to move, and yeah.
So it's a happy accident or happy byproduct?
Happy accidents, yeah. I mean, FM is a happy accident. Yeah.
So any further question?
Are there any karma questions?
Not yet. Not yet.
Let me play an example of from Sabeliev. This was the piece that I finished in 1971. And there are two aspects of this that were interesting. One was a spatial canon. So we're only hearing two channels. So these are noisy sounds. So you get the idea. So it's like the original Katya of the 14th century, where like a precursor of the fugue. And this example, which is a spectral metamorphosis, so it begins with the same kind of sound, but listen through time, this kind of noisy snare drum-like sound becomes a brass tone, brass-like tone. So what happens is the carrier modulating ratio converges from a ratio of 1.41 to 1 to 1, and it folds into harmonic series with a brass-like attack. So this was important because it showed that with frequency modulation synthesis with a large timbral space, not infinite, but maybe, I don't know, it's a big functional space, that one can create points of contact between timbres that were impossible to do in other means, and certainly in nature. So at this time, Escher was big, and his metamorphosis in the 1960s, 70s. And so finding this kind of auditory analogy to his metamorphoses, night becomes day and fish, etc.
And you do this also in phone as well, between synthesis and then the kind of like a human sounding.
Yeah, human voice sound, which rather than discrete notes becoming another timbre, but with a continuum where a bell becomes a chorus of voices. And well, I have that example. I can play that for you.
We have a couple minutes, I think, still.
Yeah. Okay.
And I remember you mentioned that you came across Stockhausen's work when you were here, and I always go back to Gesang der Junglinge. I love that piece, and I think I've heard you say that you love that piece as well. Did that have any kind of influence on this piece, or?
Yeah, well, the boy's voice, of course, and the fact that we could do these things because of the sampling theorem, and that we can make these sounds that one can imagine but can't possibly do by any other means. This cannot be done by analog means, this example. We hear a fundamental of a voice, then the harmonics, but we don't hear a vowel until the micromodulation, the mix of periodic and random vibrato. So Phoné was based upon this idea that derives from Jean-Claude Risset's work in mutations. So now we have a bell. Oops, sorry. A bell attack, which becomes a voice tone. Are we hearing? So as the bell attack begins to grow again, I add the mix of periodic random vibrato and then take it away as it decays as a normal bell. Okay, so if we make a collection of these and go from now the frequency space to pitch space, we have a bunch of bells occurring, but because they all begin together, we have here a single bell, but then each partial becomes a singing voice. And so here's the example. So it's imaginable, but can't be implemented by any other means than digital synthesis, where we have that kind of control.
I remember reading somewhere that one of your early critics was saying that you were dehumanizing music, and your response was, no, I'm humanizing computers. And I think that's a really great example of that. Also, your more recent piece, Voices, which you wrote for Maureen Chowning, who's a soprano, also here. Do you want to talk about that briefly?
So that too is based upon the same underpinnings as I used in Stria and also Phoné, by the way. But now with a singing voice, let's see. Let me bump out of this for a second. I'll play a quick example and you can see how that works. Can I? I think I can.
And for this piece, you also developed a patch in Max MSP that follows her singing voice, and it's basically a score tracking device, right? Is that right?
Yeah. So, yeah, it's a score following, not the most sophisticated that's available these days, but it works. And the program's robust, so it tracks Maureen almost without failing. She sings a pitch, a target pitch, and so the idea was the same as in Stria, But now we have a soprano, harmonic partials, mixing with complex tones, as in this case. And the surface of sound of voices is very different. So harmonic partials mix with collections of inharmonic but ordered partials, that's important. And so here's the opening of voices. So this is a ghost tone that's synthesized of the soprano. And it seems to work because good musicians tune to context. So when she hears in this odd scale that the frequency that she's looking for is in the spectrum, then she latches onto it. Well, when you think about string players playing with other string players, they tune differently than if they're playing with pianos, because the piano is fixed pitch, of course. But string quartets, they tune pure fifths and octaves, of course. So here's a completely artificial kind of spectral space where I've mixed the voice of the soprano and count on the musicianship of the performer, which is the most important thing, of course, of all, to affect make the tuning work so it doesn't sound what we think of as being out of tune, where you have kind of rough beating between partials or frequencies.
And it frees her up to kind of take liberties with time, and
Yes.
so that she's not so tied to a tape or
Right.
something that's on the grid or something
Yes.
like that.
So this was conceived in 2004, first performed in Paris. It was a commission from the Groupe de Recherche Musicale, CCRMA, and then I developed it over the next few years with a little intervening episode, but so it's now pretty robust. And we've done it in lots of places. Maybe we can do it in Berlin. So next
I have to talk
year,
to Jan about that. Maybe you guys can come back and do that.
So next year it will have been 50 years since FM was discovered.
Oh, wow. Congratulations.
Yeah, that's a good mark. Okay.
Are we out of time?
Yeah, well,
Do we have any questions from Karma?
exactly. Wait a second. So we have Chris, the current director from CCRMA, asking. Well,
Chris is asking a question.
yeah, we're all eager to hear this piece, which we heard here yesterday. Is it repeatable next month?
So Chris is wondering if the piece that you performed last night, if you can play it again next month.
Next month.
That's classic Chris, by the way.
Yeah. Well, we have to talk to Mark. We both agree that we have to do some work on the piece. We only had this one experience, and we were kind of remote from one another. But, I mean, in principle, yes. But we need to work on the piece, and will.
Great. Well, thank you.
Yeah, so I think maybe one more question, and then we have to stop for here, because we have one more talks coming up, of course. Chris says, thanks very much. Yeah, or if there's no question for now, then we leave it at that. Thank you very much, John Chowning. Thank you, Holly Herndon.